Hello everyone, I'm Norman Wahlberger. We are talking about music, foundations of music. I told you about Pythagorean approach to intervals, fundamental intervals, and connection with very simple ratios of natural numbers that really impressed the ancient Greeks. Today we want to look at this maybe from a somewhat more modern point of view, and I want to show you how our 12-tone scale, which is sort of the underlying architecture of most Western music, arises in certainly a non-trivial and perhaps almost surprising way. So I want to start with essentially just the physics of it, really just intrinsic ratios of simple things that I told you about last time. And then we're going to go a little bit beyond that and see this 12-tone structure emerging, but not in an exact fashion, sort of in an approximate fashion. So there's associated irrationalities, and so necessarily approximate quantities. So we have to make a shift from rational arithmetic, which is really a Pythagorean, fundamental tenet, to a world of, if you like, irrationalities, or if you're from my position, of just approximate statements. Okay, and this is sort of unnerving for the ancient Greeks. The Pythagoreans were very stressed out by this, but it's just the way the world is. Okay, so let me review what we were talking about last time. We were talking about strings and the relationship between the sounds produced by two strings, and we saw that the relationships of the sounds is really the same as the relationship between the frequencies formed by these vibrating strings, that these were directly related to, assuming that the strings have the same sort of physical characteristics, they have the same mass or density, and that the tensions are the same, then it all comes down to the ratio or the proportions of their extents. All right? So let's regard this interval right here, from this point B to this point C0, as sort of 1. Okay, so we have a scale up here, a linear scale, 0, 1 here, and 2 here. Okay, and so this interval from B to C is a little bit underneath. It's going from 0 to 1, and we'll think of that as sort of a fundamental string. Okay, a fundamental unit. And now we're going to make some longer strings. Okay, and then the ratios between the shorter strings and the longer string is going to represent this interval that we can hear. Okay, so the first possibility, which is sort of trivial, but it's still worth pointing out, is the unison interval, where C1 is same as C0, which is just 1. Okay, so then we just have 1 to 1, and there's really nothing to see. The next sort of simplest thing to think about is the octave, represented by this point up here. Okay, so here look at C8, which is at the point 2. So this is representing this longer string. There's a long string going from B all the way to C8, okay, in comparison to B to C0. Okay, so the relative frequencies of these things are going to be in the ratio of 2 to 1, and we're going to hear that as an octave interval. The next important one is the perfect fifth, which is represented by this thing here. Okay, and this is in the ratio of 3 to 2. See, this is at 1.5. So if we take the interval from B to C5 and compare it with the interval from B to C0, those two segments are in the ratio of 3 to 2. So if we have two strings of those extents and we compare the sounds created by them, we're going to hear a perfect fifth. Okay, so this point here is representing a perfect fifth. The next one is the perfect fourth, represented by C4, and that's in the position 4/3. So you can actually see over here what the point is. This is actually the point with x coordinate 4/3, otherwise known as 1.3333 approximately, okay? And I've just put it a little bit below. Here's the actual official x-axis. We're going to see that in a second. But this is just a little bit below it, so we can see it in reference. Okay, so this point C4 is exactly in the place where the interval from B to C4 is 4/3 the interval from B to C0. Okay, so those two strings are going to create a perfect fourth. And then C3 is our major third. Okay, arithmetically, that's 5 to 4. So again, the ratio of B to C3 to B to C0 is in the proportion 5 to 4, and that's giving us a major third. This point here, which is pretty close to it, is the minor third. That's associated to the proportion 6 to 5. Okay, so B to C3 prime to B to C0 in the ratio of 6 to 5. And there's one more, this major 6, represented by this point C6 up here. That's in the ratio 5 to 3. So B to C6 to B to C0 is in the ratio of 5 to 3. So these are almost like sort of God-given ratios or proportions, right? These are very natural from an arithmetical point of view. So these points are, somehow very simple, natural kinds of things. They're representing quantities, which are fractions, if you like. Okay, the x-coordinates are fractions, which are given by ratios of particularly simple, small natural numbers. We're always getting fractions just a little bit bigger than 1, between 1 and 2. So these are intervals that are naturally created just by the physics of strings and nice proportions. So now I want to introduce our scaling, okay, our 12-point scale. And I'm going to do that by showing you some remarkable new points. Okay, so now I'm going to show you some points up here on this top line. So there's N0, maybe N1 first. Okay, there's N1, N2, N3, N4, N5, N6, N7, N8, N9, N10, and N11. Okay, so have a look at these points. They are spaced between 1 and 2. Maybe I should make this one a little bigger. Just do that for uniformity's sake. Okay. I'm using GeoGebra here, of course. Okay, so these points that I'm creating here, they're not equally spaced. You can see that, right? The first ones are closer together, and the last ones are further apart. In fact, that's very similar to what happens in a guitar. I guess I don't have it here. But if you have a look at the frets on the guitar, you'll see that the ones close up to the neck are further apart, like these ones. And then as we get closer to the body of the guitar, they become closer together. In fact, the pattern here is exactly, or pretty well exactly the same as on the frets of a guitar, in the sense that the proportions here are all equal. So this is really a geometric series, or geometric sequence, maybe, if you like. It's not an arithmetical sequence. That would be if these things were equally spaced, but they are equal multiples of each other. And what are these multiples? Well, we can tell that because how many steps are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 steps to get up to B1. Now, if each of these are equal multiples, then basically the multiple has the property that if we raise it to the 12th power, we are multiplying by 2. Okay, so the common ratio that separates each one of these from the next is the 12th root of 2. Now that should be said in quotes, okay, because there is no such exact number. That's the way the world is, people. Sorry, but that's just the way the world is. There is no exact 12th root of 2. But, approximately we can have a look. So let's say we put 2 to the, 2 to the, 1 over 12, all right? And let's just evaluate that. Okay, what do we see? That's 1.05946, approximately. That's not it exactly. There is no such thing as it, okay? There's only some algorithm that will generate more and more digits. And these digits have the property that if you take powers of this thing, you raise it, you square it, you cube it, etc., etc. When you get to the 12th power, you're pretty close to 2. So that's how we're going from one of these to the next. We're taking the x-coordinate, in this case 1, and we're multiplying by this 1.059, etc. Okay, so that's how this sequence is created. This is very regular, very mathematical. And now we see a remarkable thing that happens. Okay? The remarkable thing that happens is that there is a reasonably close correspondence between our intrinsic, physically defined ratios given by these ratios of natural numbers and some of the entries here in this sequence. So let's have a look. Well, C0 is underneath 1, and then C8 is underneath B1. That's not a surprise. We sort of arranged that. But notice that our perfect fifth, C5 here, okay, it's pretty close to this thing that we're calling N7. Okay, if we see, you see the coordinates here, N7 is 1.49831, while C5 is 1.5. That's pretty close. Okay, that's pretty close. How about the perfect fourth? The perfect fourth, this one here, C4, is 1.333. The one above it is N5. That's 1.33484. That's also very close. Okay, so the perfect fourth and the perfect fifth are well approximated by what we're calling N5 and N7. How about our major third? Well, that's 1.25. That's 5 divided by 4. That's the coordinate. And it's not too far from N4, which is 1.25992. Okay, so we're comparing 1.25 with 1.25992. It's close, but, there is definitely a discrepancy. And what about the minor third? Well, here, this C3 prime, that's 6/5. That's 1.2 exactly. And it's reasonably close to this N3, which is 1.18921. Okay, so we're comparing 1.2 with 1.189. Pretty close, although, again, there is a noticeable discrepancy. And if we go up to the major 6, which is 5/3, so it's exactly 1.66666, or approximately in decimals. And it's pretty close to what we're calling N9, which is 1.6817. Okay, 1.666, 1.6817. So we have a kind of almost a coincidental correspondence. I mean, this is a bit of a surprise to us that if we take these powers of the approximate 12th root of 2, okay, that several of those powers are pretty close approximations to these fundamental ratios that are appearing just as proportions between small natural numbers. Okay? And that is the reason why we have our 12-tone scale. That's the reason. It's because if we create a musical system in which these are the notes, N0, N1, N2, N3, N4, etc., up to N11, and then up to the octave, then those 12 tones are going to contain within them pretty close approximations to perfect fourth here, perfect fifth, the major sixth, the major third, and the minor third. Actually, what about, down here? Well, let me introduce just a few more. Okay, so here are two more points that I can create exactly, and I'll show you what they are. So this C2 that I've cooked up here, this is the proportion 9 to 8. See how 9 to 8 is very close to N2. So 9 to 8 is roughly 1.125. That's probably it exactly, actually. 1.125. And while N2 is 1.1224. Okay, not too bad. And what about C1? Well, C1 is a little bit more curious. It's 18/17. That's maybe a bit harder to find. But we see that there's still pretty good alignment with N1. So C1 is 1.05882, while N1 is 1.05946. That's pretty close. So all of these, the ones on this scale here, all of these are given by pretty small natural numbers, although arguably this one's getting bigger, okay? And we can also cook ones up here. In fact, once you have ones down here, it's not too hard to sort of to invert the process and get ones over here. So what we end up having is a scale. This scale here is, we might say it's well-tempered. Okay, in fact, this is the origin of the well-tempered system. It's a scaling system in which the separation between adjacent notes is the same uniformly. It's always, we're just multiplying by this approximate 12th root of 2. But nevertheless, that 12-tone system, remarkably, surprisingly, beautifully, captures pretty well these fundamental intervals that are created just from the physics and the beauty of small integer numbers and their ratios. Now you might well ask, well, some of these are not that close. I mean, this one here is not that close to that one. Okay, this major 6 is not that close to that. Surely we could perhaps hear the difference. And if you are trained, you can hear this difference. Okay, and so there's still some debate as to, we're not saying this is necessarily a better system. Okay, but in practice, most people are more or less used to this system up here, and maybe might even struggle to identify these more purist, perfect ratios. But anyway, so this is, I think, a really important explanation. It is a little bit subtle, okay, but it's an explanation of why our 12-tone scale is a pretty natural thing in some sense, and where we're utilizing this sort of remarkable coincidence. Okay, we really think of it as a coincidence between these elements here and just the very particular small, beautifully numerical ratios that we get by taking proportions between small natural numbers. Okay, so this sort of irrationality here somehow coincidentally captures this thing here, and so this is the reason why guitars are the way they are and why pianos are tuned the way they are, and it's the reason why the architecture of modern Western music all starts really from this system here. And so there's this intrinsic 12-fold aspect of things. And of course, 12 is the same as the number of, our positions on a clock, okay, 1 o'clock, 2 o'clock, 3 o'clock, up to 12 o'clock. So there turns out to be this rather beautiful synchronicity between a clock and the natural 12-tone scale of our musical system. And the structure there, the number theoretical properties of this 12-fold sort of circular arrangement has huge bearing on the theoretical structure of modern music. I'm Norman Wahlberger. Thanks for listening.